So the next one is eigenvectors. Once you have the eigenvalues from the characteristic equation, the solution, you can find the corresponding eigenvectors by solving the equation a minus lambda x equal to 0 for x, and x is nothing but your eigenvector. So A is a matrix, lambda is the eigenvalue, scaling factor, and x will be eigenvector. Show x 2 by 1. So this is a column matrix. 2 1 is an eigenvector for this matrix. So this is your eigenvector. We are going to show for this matrix whether this column matrix is an eigenvector or not. We are going to show. I repeat, matrix is given. We are going to show this matrix is an eigenvector of this matrix or not. We are going to show. So the formula goes a minus lambda I x equal to 0. So ax minus lambda x equal to 0. So find out, first we will find out now ax. So a is here. This will be your x. X is nothing but eigenvector, which is nothing but x1 and x2. x1 is one component, x2 is another component. Okay. So we have ax equal to 2 minus 4, 3 minus 6, 2, 1. So 2 2s are 4, minus 4 multiplied by 1, that will give minus 4. So 4 minus 4 will be 0. 3 minus 6, again 2 3s are 6, again minus 6, answer is 0. Now we know that ax equal to lambda x according to the formula. Okay. So, but the final answer is 0. Ax equal to 0. So lambda x must be equal to 0. Correct? See, ax equal to 0. We have found out ax equal to 0. So lambda x must be equal to 0. What is lambda x? Lambda x equal to, you keep as it is lambda like this. X is nothing but 2 1. What are lambda? Lambda x equal to 0. X is there. So only possibility is lambda should be equal to 0. See, for example, 5x equal to 0. What is the possibility? 5 cannot be equal to 0. 5 is a number. Only possibility is x should be equal to 0. Similarly, lambda x equal to 0, but x is given 2 1. X is fixed. But only thing is lambda. So we discussed lambda can be 0. Can you remember? Eigenvalues. So it can stretch or it can shrink, and even it can be 0. So eigenvalue can be 0. So the example for say eigenvalue is 0 is this one. A lambda x equal to 0, 2 1, which is equal to 0 0. So thus x is an eigenvector of A, lambda equal to 0 is the eigenvalue. So eigenvalues. Let x be the eigenvector of the matrix A, then there must exist an eigenvalue lambda such that ax equal to lambda x. So ax minus lambda x equal to 0 or a minus lambda x equal to 0. So now you keep this as B. For example, a minus lambda is a totally, it's a matrix. A is a matrix. Lambda is also a matrix. See here, this is A is a matrix. We can subtract from matrix to matrix only. From matrix to matrix only you can subtract. So this must be a matrix and this must be a matrix. So together I can keep this as B. So B equals, let B equals A minus lambda I. So totally I can replace this as B. So Bx equal to 0. Now x equal to, I can bring that to that side. So B inverse 0, which is equal to 0. But an eigenvector cannot be 0. Eigenvector cannot be equal. Eigenvalue can be 0. Eigenvector cannot be 0. Thus it follows that x will be an eigenvector of A if and only if B does not have inverse, or equivalently det B equal to 0. So det A minus lambda I, which is equal to 0. So this is the proof. So this is called the characteristic equation of A. Its roots determine the eigenvalues of A. Okay. So this is the equation, and the solution of this equation will give us eigenvalues. Find the eigenvalues and eigenvectors. So we have come to the next one. First we solved characteristic equation for any matrix, and second one is eigenvalue, and third one will be eigenvector. So find the eigenvalues and eigenvectors of 1 2 1 2. So this matrix A equal to 1 2 1 2. So to find the eigenvalue, we will have to use characteristic equation. So det A minus lambda I. So det A minus lambda I will give you this expression, correct? So this is your A minus lambda I which is equal to 0. So this operation will give us 1 minus lambda, 2 minus 0, 2, 1 minus 0, 1, 2 minus lambda, 2 minus lambda which is equal to 0. So we have 1 minus lambda multiplied by 2 minus lambda, 2 ones are 2 minus 2 minus 2 equal to 0. Simplifying we will have 2 minus lambda multiplied by minus 1, so minus lambda multiplied by lambda, that will be lambda square minus 2. This 2 and this 2 will get cancelled and lambda squared is there, so this will be minus 3 lambda. I can pull lambda out, so lambda times lambda minus 3 equal to 0. It implies that lambda can be 0 or lambda minus 3 equal to 0. Is it okay? Lambda multiplied by lambda minus 3 equal to 0, it implies that lambda equal to 0 or lambda minus 3 equal to 0. So it implies that lambda equal to 0 or lambda equal to 3. So eigenvalues are 0 and 3. For this matrix, eigenvalue is nothing but 0 and 3. Is it okay? Any doubt? So now we are going to find out the eigenvector now. Okay, eigenvector. So as we discussed earlier, eigenvalue can be 0, but not eigenvectors. Eigenvectors can never be 0. So now this is the procedure for finding out the eigenvectors. See, now we have two solutions. Why two solutions? Why we have two solutions? Any idea? See, we have only two solutions here, not three solutions or four solutions. So we have only two solutions. Why? Any idea? Why we have two solutions here? Because this is 2 by 2 matrix. If it is 2 by 2 matrix, we can have only two solutions, two eigenvalues. Now, first you substitute lambda equal to 0 here. So we are going to keep this as lambda 1 and this as lambda 2. Lambda 1 equal to 0. We are going to find out the eigenvector. So this is the procedure. We are going to solve so many problems. The simple procedure is like this. A minus lambda I x times equal to 0. So this is A minus lambda I times, instead of x, as I said earlier, x1 and x2, column vector, x1 and x2. So simplifying this will give you will have to substitute lambda equal to 0 here. See, substitute lambda 1 equal to 0. So this term will go off. You will have only 1, 2, 1, 2 alone. 1, 2, 1, 2 multiplied by x1 and x2 will give you this. Now, you will have to multiply this. So that will give you x1 plus 2x2 equal to 0. Similarly, x1 plus 2x2 equal to 0. x1 plus 2x2 equal to 0 implies that x1 equal to minus 2x2. x1 equal to minus 2x2. Similarly, here too. Similarly, here also you have x1 equal to minus 2x2. Now, you keep x2 equal to 1. The minimum value, x2 equal to 1. You just keep. If you are going to keep, substitute x2 equal to 1 here, we will have x1 equal to minus 2. You substitute here. This is eigenvector. So, capital x1 equal to x1, x2, which you are going to find out, eigenvector. So, your x1 becomes minus 2, x2 becomes 1. So, minus 2, 1 is the eigenvector. For lambda 1 equal to 0, we are going to substitute for the next one. Lambda 2 equal to 3 now. You substitute the same formula. So, we are going to substitute for lambda as 3. Is it okay? A minus lambda I times x equal to 0. So, A minus lambda I times x equal to 0. So, you have 1, 2, 1, 2. Here minus 3 multiplied by 1, 0, 0, 1. So, 1 is there. Your minus 3 is there. So, you will have minus 2. 2, 0, that will be as it is 2. 1 also will be 1. But here it is 2 minus 3, that will give you minus 1 times x1 and x2. So again, so this one will give you minus 2x1 plus 2x2 equal to 0. So we have minus 2x1 equal to minus 2x2. Minus minus will go up. 2 also will cancel. So x1 equal to x2. Simple one. Substitute for x2 equal to minimum value 1. So x1 also will be 1. So your x2 will be 1, 1. So this is the complete procedure for computing eigenvalues and eigenvectors for any matrix. Simple procedure. And the same thing will be also applicable for 3 by 3 matrix, 4 by 4 matrix. Okay, only for square matrix it will work out. Any doubt? So I repeat. See here, A equals 1, 2, 1, 2. First we have to calculate the determinant first. Okay, we are going to get the characteristic equation and thereby eigenvalue equation and substitute eigenvalue equation. Okay, for lambda 1 equal to some other value, you will get one equation. You are going to solve for eigenvectors. And similarly, you just substitute another eigenvalue, substitute in characteristic equation and solve for eigenvector. So that's all. Procedure is over. Now we will go for next problem. So next problem is 1, 1 minus 2, 4. So a minus lambda equal to 0, a minus lambda equal to 0. So that a minus lambda equal to 0, that will give you this expression 1 minus lambda times 4 minus lambda. 1 2s are 2, so you have plus 2 which is equal to 0. Simplifying will give you this. So this equation is known as characteristic equation. Characteristic equation, correct? So you are going to factorize this characteristic equation. You are going to factorize. So we are going to factorize, that will give you lambda minus 3, lambda plus 2 equal to 0, correct? So 6 can be divided into 2 3's. 2 and 3, see 6 can be divided into minus 2, minus 3. This 6 can be divided into minus 2, minus 3. Minus 2, minus 3 will give you minus 5. 2 3's are 66. So you can factorize. So you have lambda minus 3, lambda plus 2 equal to 0. Lambda minus 3 equal to 0 or lambda plus 2 equal to 0, that will be eigenvalues 2 and 3. So eigenvalues are over. So characteristic equation is over. Next one is eigenvalue. Now we will go for eigenvectors. Very good. So lambda 1 equal to 2, lambda 2 equal to 3. So lambda 1 equal to 2. When lambda 1 equal to 2, we can find out the eigenvectors. So a minus lambda times x equal to 0. Use this formula. So simplifying, you will have this. So now multiplying, that will give you matrix multiplication will give you minus 1 multiplied by x1, so minus x1. 1 multiplied by x2 will give you plus x2 equal to 0. So x1 equal to x2, x2 equal to 1, x1 will be also 1. So x1 will be 1 1 in a column vector. Is it okay? Similarly, lambda 2 equal to 0, a minus lambda I times x equal to 0. A minus lambda I times. So lambda is nothing but 3. So now 1 minus 3, that will be minus 2. Here it is 0. So as it is, we have here also 0. So here minus 2. So here also 0. And this becomes minus 3. So 4 minus 3, that will give you 1. So minus 2 multiplied by x1 will be minus 2 x1. 1 multiplied by x2 will be x2 equal to 0. So we have x1 equal to x2 divided by 2. 2 minus minus will get cancelled. 2x1 equal to minus x2. Minus minus will get cancelled. See, minus 2x1 equal to minus x2. Minus minus will get cancelled. And x1 equal to x2 divided by 2. If x2 equal to 1, x1 will be 1 by 2. See, 1 by 2. If x2 equal to 1, your x1 will be 1 by 2. It is 1 by 2. Okay, it is not root 2, 1 by 2. Any doubt? So your x2, the another eigenvector equal to 1 by 2, 1. Now we will go for next problem. A equals minus 3, 15, 3, 9. So a minus lambda I, use the formula. So simplifying, you will have this. You can get the characteristic equation and you will have to factorize. So minus 72, 6 12s are 72. 6 minus 12 will give you minus 6. So we can factorize this equation. So this is the characteristic equation. And after factorizing, you will have eigenvalues, which is nothing but lambda equal to minus 6, 12. So we will have to substitute lambda 1 equal to minus 6 in the eigenvalue equation, in the characteristic equation. So we have a minus lambda I times x equal to 0. So here a is here, lambda, you will have to substitute lambda equal to minus 6. So I have multiplied with minus, that will give you plus. So plus 6 0 0 6. Simplifying, that will give you 3 15 x1 x2. I can pull 3 out here. I can pull 15 out here. in the column. Is it okay? So I can pull 3 out here. It's the same number. I can pull 15 out here. So 3 15s. And here 1 1 1 1. x1 and x2. So we have x1 plus x2 equal to 0. So it implies that x1 equal to minus x2, x2 equal to 1. That will give me x1 equal to minus 1. See? Either way you can go. If x2 equal to 1, you can have either way. See, if x2 equal to 1, then I will have to write x2 as 1 and this must be minus 1. You can write either way, doesn't matter. If x1 equal to 1, x2 becomes minus 1. Answer is the same. Okay, 1 minus 1. Now for lambda equal to 12, to find the eigenvectors a minus lambda I times x equal to 0, the same formula you have used. Simplifying, you will have this. I have pulled minus 15, see 15 out. I have pulled 3 I have pulled 3 out, so that will give you minus 1 1 1 minus 1 x1 and x2 minus x1 plus x2 equal to 0. That will give us x1 equal to x2. For x2 equal to 1, x1 will be also 1. So eigenvectors are 1 1. Okay, find the eigenvalues of A, that is to find lambda such that det A. So we are going to find out the eigenvalue again for 2 by 2 matrix. We will have to find out the characteristic equation, solve the characteristic equation, factorize the characteristic, that will give you eigenvalue. So A minus lambda I, A minus lambda times I, simplifying you will have this, take the determinant which is equal to 0, so that will give you characteristic equation. Lambda squared minus 4 lambda minus 5. So now you are going to factorize. Minus 5 is there. So you are going to factorize. So minus 5 multiplied by plus 1 will give you minus 5. Minus 5 plus 1 will give you minus 4. So minus 4. So this is the idea to factorize, correct? You just take the last number which is nothing but minus 5. You just choose two numbers. On multiplication you should get this. On addition you should get minus 4. I repeat, see 5 is there, minus 5 is there. You choose two numbers. I have chosen minus 5 and plus 1. 5 minus 5 and plus 1 will give me minus 5. See, on multiplication we will give this number. On addition, minus 5 plus 1 will give me minus 4. So that's the idea. So lambda minus 5, lambda plus 1 which is equal to 0. So lambda equals minus 1 and 5 are eigenvalues. So how many eigenvalues we can have? Only 2, because this is 2 by 2 matrix. 2-dimensional matrix example. Again one more example. A equals 2 1 1 2. So you have to use determinant A minus lambda equal to 0. So we have 2 minus lambda multiplied 2 minus lambda minus 1. So we have lambda squared minus 4 lambda plus 3 which is equal to 0. See, I have chosen like this 3. On multiplication you will get this. On addition you must get this. So factorizing, that will give you eigenvalues 1 and 3. So those two are eigenvalues and this will be your characteristic equation. Okay, lambda squared minus 4 lambda plus 3 equal to 0 will be your characteristic equation. Eigenvalues, another example. A equal to 2 minus 12, 1 minus 5. Use A minus lambda equal to 0. But here I have chosen as C, lambda I minus A equal to 0. Det lambda I minus A equal to 0. Earlier we started with A minus lambda equal to 0. Okay, but det is there. So almost it's the same. Is it okay? Det is there. So lambda I minus A equal to 0. We are going to substitute lambda minus 2, 12 minus 1 lambda plus 5. Then simplifying you will get lambda plus 1, lambda plus 2 and lambda equals minus 1, lambda equals minus 2 will be your eigenvalues. The roots of the characteristic equation can be repeated. So possibility is there. The roots, it can be repeated. 2, 2, 1, 1. It can be repeated. Say lambda 1 equal to lambda 2, it can be repeated. Suppose if it is so, we call this as multiplicity of K. For example, we just take 3 by 3 matrix. Okay, the roots can be repeated. The roots are different. Here it is minus 1, minus 2. They are not the same. It can be repeated also. Minus 1, minus 1, minus 1 can be repeated. But here they are not repeated. But here in this case, look at this case, we have lambda minus 2 whole cube equal to 0. What are the roots? Lambda equal to 2, 2, 2. See, we need to have 3 roots, correct? 3 by 3 matrix. We need to have 3 roots. But lambda 2 is the eigenvector of multiplicity 3 times. Okay. A equal to 1, 2, 3, 0, 4, 5, 0, 0, 6. Find the eigenvalues of A. So, simple to know. But here it is 0, 0, 0. What is this matrix called? Any idea? This matrix is called? Very good. So, upper triangle matrix. Good. So, you can have 1 minus lambda multiplied by 4 minus lambda multiplied by 6 minus lambda, and 1, 4, 6 are your eigenvalues, 3 eigenvalues. So, find the eigenvalues only asked. It's a very simple one. Okay. Now, find the eigenvalues and normalized. So, little bit difficult. Normalized eigenvectors. So, earlier we calculated only simple eigenvectors. Now we are going to compute normalized eigenvectors. Only small modification. Let us see. So we have 3 by 3 matrix, and we are going to follow another method. Correct? So instead of lambda minus I equal to 0, we are going to follow this method. Lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0, where s1 is the sum of main diagonal elements, s2 is sum of cofactors of minus of main diagonal elements, and s3 will be determinant. So your s1 will be 1 plus 5 plus 1, 7. Your s2 will be sum of minus of main diagonal element. The first one will be 5, 1, 1, 1. See, 5, 1, 1. Second one will be for 5. So 1, 3, 3, 1. And third one will be 1, 1, 1, 1, 1, 1. So easily you can get the determinant and sum. Okay. So s2 will be 0. What about s3? S3 determinant is very simple. So we have the determinant, and we can calculate the value of the determinant. That gives us minus 36. Substituting in this expression, okay, in this equation we have lambda cube minus, instead of s1 is already 7 we calculated, so minus 7 lambda square plus 36 equal to 0, because s2 equal to 0. So s2 equal to 0. So there is no lambda here. See, there is no lambda here. To find the eigenvalues, we have to factorize the above equation. So this is third term. See here, it is not two terms. This is lambda. It is not lambda square. It is lambda cube. We need to have 3 eigenvalues. Correct? 3 eigenvalues. So we have this equation: lambda cube minus 7 lambda square plus 36 equal to 0. So we know already this method. Probably we would have learnt in plus 2. So what we can do is 1 minus 7. There is no coefficient of lambda square, so 0. The last one is 36. 6, 6 are 36. So I have written as 6, which we learnt in lower classes. Then you just subtract this. So this becomes 1. 6 multiplied 1 will give you 6. You subtract this. So that will give you minus 1. 6 multiplied minus 6 will be minus 6. You add this, that will give you minus 6. 6 minus 6 will give you minus 6. You just add this, will give 0. So 6 is a 1 factor, because it becomes 0 here. And this becomes lambda square minus lambda minus 6. So lambda minus 6 is 1 factor. Lambda, because we are able to get only 0 here. If it is not 0, then it is not a factor. Okay, so we have lambda minus 6, lambda square minus lambda minus 6 equal to 0. This is 1 factor. Now we are going to factorize this. Easy to factorize. Minus 6 can be separated into minus 2, minus 3. See, minus 2, plus 2, minus 3. This minus 6 can be factorized into minus 3 plus 2. Minus 3 multiplied by plus 2 will give you minus 6. Minus 3 plus 2 will give you minus 1. See, minus 1 is here. Is it okay? So you can factorize. So lambda minus 3, lambda plus 2, which is equal to 0. So your factors will be, eigenvalues will be 6, 3 and minus 2. So they are all eigenvalues of this equation. Now we are going to find out eigenvectors. Our aim is to find out normalized eigenvectors. Correct? So we calculated characteristic equation. We computed eigenvalues. Correct? We have computed eigenvalues. Next one is we are going to calculate eigenvectors. Then after that, normalized eigenvectors. So to find out the eigenvectors, a minus lambda x equal to 0. So this is your eigenvector, which is equal to 0. A is given as this, and of course a minus lambda a. So this must be 1 minus lambda, 5 minus lambda, 1 minus lambda. You have to substitute the first eigenvalue. First eigenvalue is 6. So lambda 1 equal to 6. You substitute here. So we have 1 minus 6, 1, 3, 1, 5 minus 6, 1, 3, 1, 1 minus 6. Simplifying, you will have this. Okay, now minus 5 multiplied by x, 1 multiplied by y, 3 multiplied by z. In earlier problems, we had x1, x2, x3. Can you remember for 2 by 2 matrix? We said x1 and x2, both are the same. Here you have written as x, y, z. Even if you write x1, x2, x3, doesn't matter. Okay, so now, so we have three equations as I said. See, minus 5x plus y plus 3z equal to 0. So this is first equation. Second equation, third equation. We are going to get the values of x, y, z to have eigenvectors. So now again, probably you would have studied in lower classes. I will teach you in a simple way. You just take the second number, second coefficient. So what is the second coefficient? 1. This is 1y, 3, and next one is minus 5. Take this coefficient here. You write x, y, z here. Then here you write the second coefficient, third coefficient, first coefficient, again second coefficient. It's very simple one. We are going to get x, y, z value. Now for this one, the second coefficient will be minus 1. See, minus 1. Third coefficient will be plus 1. First coefficient will be 1. Second coefficient will be minus 1. Now you just take 1 multiplied by 1 minus 1 multiplied by 3. So x divided by, this is not divided by, x by 1 multiplied by 1 will give you 1. 3 multiplied by minus 1 will give you minus 3. Only one minus is there. So plus 3. So x divided by 4. And this will be y for y. 3 multiplied by 1, 3. 1 multiplied by minus 5, minus is there. So plus 5. So y divided by 8. And this will be z divided by 5 minus 1, z divided by 4. This is the value of x, this is the value of y, this is the value of z. Otherwise, we can solve this equation. We can solve this equation. How to solve this equation? You multiply this by 5. So this becomes 5x minus 5y plus 5z. You add these two. 5x and minus 5x will get cancelled. You have two equations. Is it okay? Y plus z. Here also you multiply by 3 and subtract this. 3x minus 3x will cancel. You have y and z. So we have 2y and z. Again you will have to multiply with the same number. Get rid of any one of the vectors. You can get either y or z. Either way you can do it. But this is simplified one. So you have 4, 8, 4. Multiples are there. I can write this as divide by 4. That will give me 1. Divide by 4. That will give me 2. Divide by 4. That will give me 1. So x, 1, y, 2, z value. So this is your eigenvectors. So x, y, z nothing but 1, 2, 1. 1, 2, 1. So x1, x2, x3 or x, y, z. So they are all 1 to 1. What is this one? x1 equal to column vectors 1 to 1. What is that called? Eigenvectors. Eigenvectors for eigenvalue lambda 1 equal to 6. Correct? For eigenvalue, we are able to get now not normalized. This is not normalized. This is ordinary eigenvector. To get normalized eigenvectors, you just square and take the root. Just take the square. See here. Take the root, square it. So that will give you 1 square plus 2 square plus 1 square equal to root 6. You divide by root 6, that will give you normalized eigenvectors. That's all. Simple one. See, 1 by root 6, 2 by root 6, 1 by root 6. So this is your normalized eigenvector, not normalized eigenvectors. So we had a matrix, 3 by 3 matrix, and next step is the characteristic equation. We solved for the characteristic equation which is equal to 0. We are able to find out the eigenvalue. We used one eigenvalue to get eigenvector. Then after that we have normalized. So we are able to get normalized eigenvectors. Any doubt? Okay. Any doubt? Okay. Now similarly we can go for lambda equal to 3, the second eigenvalue. So lambda equal to 3. Lambda equal to 3, the matrix becomes So we have A minus lambda equal to 0. The same formula we are going to use. So we have this matrix which is equal to 0. As usual, we are going to have three equations. We are going to solve the same method. We are going to follow 1, 1, 3, minus 2, 1. See, x, y, z. Those equations are there. 1, 3, minus 2, 1, 2, 1, 1, 1, 2, x. Then 1 multiplied 1 minus 3 2s are 6. X divided by 5 minus 5, y by 5, z minus 5. See, they are all equal, so we can divide equal number. So we can have minus 1, 1, minus 1. Suppose if it is minus 4, 4, 3, you should not divide by as it is. You have to write as it is. If it is equal number or if it is multiple, then we can divide by the same number. We can have. So the values, the eigenvectors will be minus 1, 1, minus 1. Very good. Minus 1, 1, minus 1. So this time we have written in a row vector. We can write either way. We can write either in a column vector or a row vector. So last time we wrote in a column vector, but this time we have written in a row vector. Doesn't matter. Everything is the same. We can represent vectors, eigenvectors in a row size or column wise. Doesn't matter. So now normalized eigenvectors, we have to square it and take the root for each component. So you have minus 1 squared plus 1 squared minus 1 squared, they will give you root 3. So minus 1 by root 3, first eigenvector, second eigenvector, third eigenvector. So this totally that will give the normalized eigenvector for the second eigenvalue lambda 2 equal to 3. Now we will go for the lambda 3 equal to minus 2. The same procedure A minus lambda equal to 0. So we have this one which is equal to 0. The same procedure, we have solved three equations. We will have to go with the same procedure. So you will have x divided by x 20 minus 20, y by 0, z by 0. So now we can go with same numbers. Here you have minus 1, 0, 1. So eigenvectors will be minus 1, 0, 1. Normalized eigenvector will be root of minus 1 squared plus 0 squared plus 1 squared. So root 2. So minus 1 by root 2, 0 by root 2, 1 by root 2. So this is the way to compute normalized eigenvectors. Any doubt? So eigenvalues and eigenvectors of 3 by 3 matrix. The same procedure, but this is not normalized. So ordinary one. So 3 by 3 matrix, and we have A minus lambda equal to 0. So here written as M minus lambda equal to 0. Determinant, you have to take the determinant. Determinant, you are going to take the determinant. We have taken, we have simplified, and we are able to get the characteristic equation. And solving this characteristic equation will give you eigenvalue. This is your assignment. So you have to solve this characteristic equation to get the eigenvalue 1, 2, and 3. Okay, you just try. How to try? The simple example will be, you substitute first lambda equal to 1 here. You just guess. So it will be like this one. You lambda equal to 1. You substitute lambda equal to 1 here. 1 minus 6 plus 11 minus 6. What is the value? 1 minus 6 will be minus 5. 11 minus 6 will be plus 5. Minus 5 plus 5. So lambda equal to 1 will be an eigenvalue. It's a solution. That is the idea. You substitute and get. You just try. You will get it. So it will be always 1, 2, 3. Surely it will be like this. Okay, you try for 2, again you will get it. So if you are able to get 1, it's easier to go for 2 and 3 easy. It is very difficult. Whereas second quadratic equation will be very easy. If it is lambda squared, it will be very easy. Lambda cube will be very difficult. For that, it's a good suggestion. Okay, so that is your assignment. For each eigenvalue lambda, find the corresponding eigenvectors by solving m minus lambda equal to 0 for non-zero. So this is the procedure which we have gone for this. This is the procedure. So m minus lambda I x time equal to 0. So we have three equations. So this time I have done in a different way. See, look at this equation. We have done in a different way. X minus y plus 6z is equal to 0. Instead of this method, see, instead of this method, we have used in a different way. See here, we are going to multiply this equation by 3. So that will give you 3x minus 3y 18z. But 3x is already, see 3x is there. You just subtract it. I repeat, see here, this equation we are going to solve. Okay, these three equations we are going to solve. I am going to multiply the first equation by 3 and subtract this equation. 3x, 3x will be cancelled. This is what I said earlier. So you will have only y minus 9z. See, when you are going to subtract, y minus 9 is equal to 0. It implies that y equal to 9z. Y equal to 9z. So substituting equation 1, which we have already done. So that will give us x minus 9z. Instead of y, you can substitute 9z plus 6z. So this becomes 3z. So x minus 3z, which is equal to 0. So x equal to 3z. You substitute z equal to 1 as usual. So x becomes 3 3s are 9. See, 3 x is 3z equal to 1. X equal to 3. X equal to 3. Substitute z equal to 1. You will have x equal to 3. If x equal to, then z equal to 1, that will be y equal to 9. So 3, 9, 1. So that will be your eigenvectors. So this is another. So lambda, for lambda equal to 2, you will have the eigenvector like this. Lambda equal to 3, you have eigenvector. So those will be your assignments. Okay. The same procedure, you can follow this procedure, or even you can follow this procedure. And you have to get the answers as 161, 151. How to find the normalized eigenvector for this? Any answer? How to find it? This is not normalized. How to find out the normalized eigenvector for this? Root of 1 squared plus pi squared plus 1 squared. Pi 5, 25. 25 plus 1 plus 1. So 27. So 1 by root 27, 5 by root 27, 1 divided by root 27 will be your normalized eigenvectors. Simple. So find the eigenvalues and corresponding eigenvectors. So this also will be your assignment. You try. So you have matrix A, and characteristic equation is given by this. We have factorized and we are able to get eigenvectors like this for each eigenvalue. So we have 3 eigenvalues, 1, 2 and 3. You can have eigenvectors like this. So that will be also your assignment. Okay. I have also done. I have also simplified for you. See, I have simplified lambda cube minus 6 lambda. See, 1, 2 minus 1 lambda minus lambda equal to 0. And I have used only third column, and I have done simplified. I am able to get this equation. So this will be your characteristic equation, and so this is your characteristic equation. See here, and we are able to get the eigenvalue. So that will be your assignment. Okay. The last session will be properties of eigenvalues and eigenvectors. So which is very important question. Probably you should know. Definition: the trace of a matrix A designated by trace of A is a sum of elements in the main diagonal. We know already. Trace of a matrix is the sum of main diagonal elements. First property: the sum of the eigenvalues of the matrix equals to the trace of a matrix. Of course we know. Property 2: a matrix is singular if and only it has a 0 eigenvalue. Okay, 0 eigenvalue. The eigenvalues of an upper or lower triangular matrix are elements on the main diagonal elements. Okay, so we have only main diagonal elements. Okay. Property 4: if lambda is an eigenvalue of A and A is inverse, then 1 by lambda is an eigenvalue of matrix A inverse. Invertible means inverse. Property 5: if lambda is an eigenvalue of A, then k lambda is an eigenvalue of Ka, where k is any arbitrary scalar. So like lambda. Lambda is an eigenvalue of A, then lambda to the power k is an eigenvalue, then A to the power k will be a positive value, positive integer of k. If lambda is an eigenvalue A, then lambda is an eigenvalue of A transpose. The product of the eigenvalues, okay, of a matrix equals to the determinant of the matrix. So this is the last property. So we are going to wind up. Let us see in the next class. Bye students.